So to get the total jump distance, I essentially did the same thing as I did to get the takeoff distance. So using that data point that I dropped from his front foot on takeoff, I did the same thing and I did frame by frame over the whole jump, and then dropped another data point when his hind leg first hits the ground, which is there. I don't know if you can see it, but I'll drop another one. There. So then I connected the two data points, this hunter all the way to this blue color right there. And then found that total jump distance to be 2.04 meters. 2.034 meters. So the last clip of Ego was a pretty ideal jump. And I wanted to show a little variation in how the jump takeoff distance from the jump relates to the total jump length. So in this situation, Ego took off from a much greater distance from the fence. He took off at a distance of 1.311 meters. So that's about double, that's over double the distance than the last jump. So I placed a diddy point there and let him jump. And then measured the total jump distance. So from this red data point all the way to his hind hoof right there at the white sock. And that distance was 2.847 meters, which was a much greater distance than his ideal jump prior. Okay, now that I've shown an ideal jump and then a long jump, I want to show what happens when there's a short jump. So I did the same process and see his hoof right there. There was a red data point was placed. Frame by frame, I went over the jump. And there. And then there's, you can see the other red data point that I placed prior. And I connected the two and found that the total jump distance was 1.758. So we can see that the relationship between a long jump, a long distance from the jump equals a long total jump, and a short distance from the jump equals a shorter total jump. To get the jump angle, I did the following process. So you can see his cannon bone right here. His hind cannon bone is pretty straight, and you can see the frame before and the frame after that it's no longer as straight. So I found that one frame that was pretty vertical and dropped the axis right in line where his hoof meets the ground, right beneath this fetlock joint. An axis is just a frame of reference. And then I allowed him to take off a little more, and I found the point at which the blue dots, and the blue dots are the data points, are placed at the point of his shoulder, so where his humerus meets his scapula right there, that point of his shoulder. And I found the point at which it gave me a nice straight and linear relationship. So before it starts curving over as it does right there. And you can see this frame right here gives it to us. And then as I took the measuring tool, again as a reference point, not to actually measure, to give me a nice straight line, I placed at the origin and connected it to that blue dot. And it gives me the measurement, but I just disregard that. And instead I take a screenshot of it and then transfer that image over to the online protractor that I'm using. And you can see I did some protracting there and got myself the angle. So I just laid this green line right in line with the line I laid on Logger Pro, and then laid this other green line right on the axis and found that the angle was 40 degrees. So angles are very important in horse jumping. So I wanted to kind of show some of the variation I got with a few of the clips of Ego jumping. So the jump prior was a pretty ideal jump, but this jump, Ego took off over a meter away from the fence, so it was a pretty large jump distance. And you can see that from where his hind foot is to where his peak jump is, it's a 37-degree angle. the jump prior was a 40-degree angle. In this photo, the horse is taking off at a much closer distance to the fence. So naturally, because the distance is shorter between the takeoff and the fence, the horse has to clear a greater height in a shorter amount of time. So the takeoff angle is much greater than a horse that took off from a further away distance. And you can see that there is a 5-degree difference between a horse who took off a meter away versus a horse who takes off 0.1 meter away. And this is just clear evidence with Ego and my data. After collecting all this data, I did some analysis and put together 2 graphical models of horse jumping and how the distance from the jump can affect the jump angle and can also influence the total length of the jump. So you can see here that there is an indirect relationship between the distance from the jump and then the jump angle. So as the distance from the jump increases, the jump angle decreases. From this model, you can see how the distance from the jump affects the total jump length, and it is a direct relationship. So as the distance from the jump increases, the total jump length will also increase. And we saw this with Ego and his ideal jump, his short jump, and then his really long jump. For the second part of my experiment, I'm going to analyze how velocity at takeoff can influence the jump. However, doing this, I kind of noticed that there was no really significant findings with takeoff velocity comparing to the beauty of the jump or the smoothness of the jump, because all of the horses approached at a different initial velocity. However, I did notice that there was a relationship between takeoff velocity and landing velocity. So I'm going to show you a little bit about how I found takeoff and landing velocity and then what my findings kind of showed. So to find the takeoff and landing velocity, I used a distance versus time graph and then found the slope at the points where the horse was taking off and the horse is landing. That will give me the velocity. However, the horse is taking off at an angle and is not moving in a strictly horizontal or vertical pattern. So I had to use the angles that I achieved for the previous part of the experiment to plug that into a equation to get the velocity at an angle. So in order to get the velocity, I chose to put the data points at the point of shoulder. So this is where, again, the scapula meets the humerus, and I chose to put it there because that's a pretty predominant point that's easy to see throughout the whole flow of the jump. It's easy to make a consistent data point, so if I can have a pretty clear spot of where to place them. I also chose this spot because it's consistent with the horse's total motion. It's not on a leg, which is moving in a different direction and fashion than the actual horse is moving. So I chose to put them at the point of the shoulder. And then to get the velocity, I needed to find the slope of this distance versus time graph. So I found the points where the horse was in the air and moving over the jump. So I found the exact moment that the horse's leg comes off the ground, and it's right about there. So I made a time reference right there, so 2.067, and then keep following it up until the points level out and then turn in the negative direction. So right about there is when the points are still moving in a pretty linear fashion. So then I highlighted all those, and then I do analyze linear fit, and I find the trial right there, and that is my x velocity at the time that the horse is taking off. However, this is not the velocity of the horse at takeoff because I need to use the angles that I achieved earlier and plug that into a cosine trigonometric